Hello students, this is Professor Chalai, and in this video we're going to look at heat from chemical reactions. As always, you can follow along with our chapter 5 workbook, and since you technically have all the knowledge you need to go ahead with numbers 10 and 11, you can pause the video now and try to work them out on your own. Otherwise, I will work them out for you. But these two questions are dealing with heat from chemical reactions. So far, we talked about how the heat from the system is going to be negative the heat from the environment. So if you have two substances in thermal contact, they'll exchange heat until they both come to the same final temperature. But what if instead of two different substances at different temperatures, you just have a reaction happening that can either absorb heat or release heat? This reaction, if it releases the heat, that heat will go into the environment. Usually it's the solution, the water that the reaction is happening in. Or if it absorbs heat, that heat came from the solution or the environment that the water is absorbed in. So it's the same setup, except our system that we're interested in now is now a reaction that's releasing or absorbing heat. So let's see how we might work out such a problem. So in this number 10, they tell us that we have 50 mils of one solution and 50 mils of another solution, both starting at 22.0 degrees Celsius, and they're added to a coffee cup calorimeter. The temperature of the mixture reaches a maximum of 28.9 degrees. So after you mix these two, a reaction happens, and then the final temperature of the solution increases to 28.9 degrees. This means that the reaction gave off heat into the environment, the solvent that the reaction is happening in. So the question is, what is the amount of the approximate amount of heat produced by the reaction? So let's figure that out. So we know that the heat for the reaction will be negative the heat for the environment, the solvent. So let's find the heat for the solvent. So we know that the heat will be equal to the mass times the specific heat capacity times the temperature change. So let's see if we have all of these pieces of information. We have the final temperature and the initial temperature, so we can calculate the temperature change. Do we have the mass? No, we don't have the mass, but the mass of the solution, but we have the volume of HCl and the volume, no, not there, sorry, the volume of NaOH. So the total volume of the solution will be 100.0 mils, right? 50 mils plus 50 mils. And we're going to assume that the solution has the same density of water, just to make our calculations easy. And so the density of water is 0.997 grams per milliliter. So the mass of this setup is just going to be 99.7 grams. So using that and making the assumption that it has the same density as water, we can find the mass of the solution. We know the specific heat capacity of water, which is 4.18 joules per gram per degree Celsius. That's another assumption that we're going to make. We're going to assume that this solution, that's the solvent, is water, because any solution, there are going to be billions of water molecules for every one solute molecule. So we can pretty much assume that the specific heat capacity of that solution is the same as the specific heat capacity of water, because they didn't tell us otherwise. And the temperature change, we can find it's just going to be 28.9 degrees Celsius minus 22.0 degrees Celsius, which gives us 6.9 degrees Celsius. So we have all of the pieces of information that we need to solve for the heat from the environment, which is this solution. The heat from the environment then will be 99.7 grams times 4.18 joules per gram per degree Celsius times the temperature difference of 6.9 degrees Celsius. So degrees Celsius cancels out, grams cancels out, and we're left with the two significant figures, a heat for the environment of 2900 joules, which is the same as 2.9 kilojoules. But that's the heat from the environment. The heat for the reaction, remember, is negative the heat from the environment. So the heat from the reaction will be minus 2.9 kilojoules. The assumptions that we make here made here was that the total volume was just the volume of the two solutions added together, that the density of the solution is the same as the density of water, and that the specific heat capacity of the solution is the same as the specific heat capacity of the water. All right, hopefully that gives you some clues now. We can find heat of reaction by finding the heat for the environment, which is usually the solvent that the reaction is happening in, made up of mostly water. Try number 11 by yourself if you haven't yet, and then pause the video and I'll go that over with you. Okay, so number 11 is very similar. We have 100 mils of some salt, and we have 100 mils of another salt, and they're both starting out at 21.9 degrees Celsius. They're mixed together, and then the final temperature increases to 23.5 degrees Celsius. And we have a precipitate, right? So the question is, how much heat is produced by this precipitation reaction? And then there are additional questions like, what assumptions did you make? Okay, so we know that this reaction, Q for the reaction, is going to be equal to negative the Q for the environment, which is made up of the water, the calorimeter. So let's see if we can find the Q for the environment. So the Q for the environment will be the mass of the environment times the specific heat capacity times the temperature change. The mass will be, we're just going to assume the total volume is going to be 200 mils, and the density is the same as that for water, so 0.997 grams per mil, which will give us a mass of 199.4 grams. Right, this is going to be to 1 sig fig because 100 plus 100 is 200, but only 1 sig to 1 sig fig. Okay, the specific heat capacity, again, these are aqueous solutions, so the solvent is water. We're just going to use the specific heat capacity of water, which is 4.18 joules per gram per degree Celsius. And the temperature change is going to be 23.5 degrees Celsius minus 21.9 degrees Celsius, which gives us... let's see if I can do that math. 22, 23, 2, 1.6 degrees Celsius, I think. Okay, so now that we have the mass, the specific heat capacity, and the temperature, we can find the Q for the environment as 199.4 grams times 4.18 joule per gram per degree Celsius times 1.6 degrees Celsius, which cancels out nicely to give us an answer of, rounded to 1 sig fig, right? Because our mass is actually 1 sig fig. We get an answer about 1,000 joules or 1 kilojoule. And so the Q for the reaction, the heat from the reaction, is negative 1 kilojoule. Note that if the reaction, heat from the reaction is negative, it means the reaction lost heat, which makes sense. The reaction lost heat, the heat was gained by the water, and so the water temperature increased from 21 degrees or 21.9 degrees to 23.5. So the sign is very important. Negative means something lost heat, positive means something gained heat. All right, that'll bring us to the end of looking at heat from chemical reaction. We're actually going to look at this in a little bit more detail in our next set of lectures. But in our absolute next lecture, we're going to look at bomb calorimetry and some calculations from that. I'll see you then. Bye.